The electric heating industry, while mature, still sees ongoing research and development to boost efficiency and discover new technologies. Resistive heaters, commonly using nickel-chromium wire, are the subject of studies into alternative alloys and composite materials. The goal is to find materials with higher electrical resistance, less oxidation, and better thermal conductivity, ultimately increasing heat output and efficiency. Heat pumps offer an efficient heating method by transferring heat from a low-temperature source to a high-temperature one. Recent improvements include variable speed compressors for better energy efficiency, refrigerants with lower global warming potential, and dual fuel systems that integrate heat pumps with gas heating for optimal performance. Semiconductor-based heating uses thermal-electric devices to convert electrical energy into heat. While these devices can consume a lot of energy, research is aimed at improving their efficiency and lowering their costs. Other technologies include infrared heaters, which emit electromagnetic waves to directly heat objects and surfaces, providing targeted warmth. Induction heaters use a magnetic field to induce electrical currents in metal cookware, generating heat directly. Plasma heaters superheat ionized gas to produce intense heat. The idea of using pressurized gases for electric heating has been considered, but faces challenges related to efficiency, safety, and practical application. High calorie output would require extremely high gas temperatures, needing specialized equipment and materials. With growing concerns about climate change, it is increasingly important to develop electric heating technologies that minimize greenhouse gas emissions. This includes research into renewable energy sources like solar and geothermal, and the integration of heat pumps with electric vehicles and smart grids. In summary, even with well-established technologies in place, the electric heating industry continues to explore innovative solutions to improve efficiency, reduce costs, and address environmental concerns. The aim is to improve heat output and efficiency of the resistance elements. Firstly, heat pumps are an efficient heating technology that uses electricity to transfer heat from a low-temperature source, such as outdoor air, to a high-temperature source, such as a home. Secondly, advancements in heat pump technology include variable speed compressors for improved energy efficiency. Thirdly, refrigerants with lower global warming potential are being developed. Fourthly, dual fuel systems that combine heat pump and gas heating for optimal performance are being created. Thermal-electric devices convert electrical energy into thermal energy and have been explored for heating applications. While thermal-electric devices have high energy consumption, research focuses on improving their efficiency and reducing costs. Infrared heaters emit electromagnetic waves that directly heat objects and surfaces, providing targeted warmth. Induction heaters use a magnetic field to induce electrical currents in metal cookware, generating heat. Plasma heaters superheat ionized gas to produce intense heat. The concept of using pressurized gases for electric heating has been explored, but challenges remain in terms of efficiency, safety, and practicality. To achieve high calorie output, gases would need to be heated to extremely high temperatures, requiring specialized equipment and materials. As concerns about climate change intensify, the development of electric heating technologies that minimize greenhouse gas emissions is becoming increasingly important. Research focuses on renewable energy sources such as solar and geothermal energy, as well as the integration of heat pumps with electric vehicles and smart grids. It's important to remember that electrical work should only be performed by qualified and licensed electricians to ensure safety and compliance with local electrical codes. When working with electrical circuits, always follow safety procedures such as turning off the power at the breaker before working on any electrical components, testing circuits for voltage before touching them, and using appropriate personal protective equipment. Understanding the NEC, or National Electrical Code, is crucial for electricians. The NEC provides guidelines and regulations for safe electrical installations. Electricians must be familiar with the specific articles and sections of the NEC that pertain to the type of work they are performing. For example, Article 210.8 covers ground fault circuit interrupter, or GFCI, protection requirements, while Article 250 discusses grounding and bonding. Sizing conductors correctly is essential to prevent overheating and ensure that electrical circuits can handle the intended load. The NEC provides tables and guidelines for determining the appropriate conductor size based on the ampacity of the circuit and the type of insulation used. Factors such as ambient temperature and the number of conductors in a raceway can affect the ampacity of a conductor, so these must be taken into account when sizing conductors. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and reduce the efficiency of electrical systems. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Electricians must calculate voltage drop to ensure that it stays within acceptable limits. Grounding and bonding are critical for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and energize the circuit. Bonding connects metal parts of the electrical system together to create a low impedance path for fault current. The NEC provides detailed requirements for grounding and bonding, which electricians must follow carefully. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices must be properly sized and selected to coordinate with the conductors they are protecting. Electricians must understand the different types of overcurrent protection devices and their characteristics to ensure that they provide adequate protection. Electrical enclosures, such as junction boxes and panel boards, must be properly installed and grounded to protect against electrical shock and prevent the spread of fire. Enclosures must be sized appropriately for the number of conductors and devices they contain, and they must be installed in accordance with the NEC. Wiring methods, such as conduit, cable, and surface raceway, must be selected and installed in accordance with the NEC. The choice of wiring method depends on the application, the environment, and the type of conductors being used. Electricians must be familiar with the different types of wiring methods and their installation requirements. Electrical equipment, such as motors, transformers, and lighting fixtures, must be installed and connected in accordance with the manufacturer's instructions and the NEC. Electricians must understand the electrical characteristics of the equipment and ensure that it is properly grounded and protected. Electrical testing and troubleshooting are essential for ensuring the safety and reliability of electrical systems. Electricians use a variety of test instruments such as multimeters, clamp-on ammeters, and insulation resistance testers to diagnose electrical problems and verify the proper operation of electrical equipment. For example, understanding alternating current, or AC, circuits is fundamental. In AC circuits, voltage and current vary sinusoidally over time. Key concepts include frequency, measured in hertz, which represents the number of cycles per second, and root mean square, or RMS, values, which represent the effective values of voltage and current. Understanding three-phase power systems is important for working with high-power electrical equipment. Three-phase systems provide a more efficient and stable power supply compared to single-phase systems. Key concepts include line voltage, phase voltage, and the different types of three-phase connections such as Y and delta. Power factor is a measure of how effectively electrical power is being used in an AC circuit. A low power factor can result in increased energy costs and reduced system capacity. Electricians should understand the causes of low power factor and methods for improving it, such as using power factor correction capacitors. Harmonics are distortions in the sinusoidal waveform of voltage and current in an AC circuit. Harmonics can be caused by nonlinear loads, such as electronic devices and variable frequency drives. Excessive harmonics can cause equipment to overheat, misoperate, and fail. Electricians should be able to identify and mitigate harmonics using filters and other techniques. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, power line disturbances, and switching events. SPD diverts surge current to ground, preventing it from damaging sensitive electronic components. Electricians should understand the different types of SPD and their installation requirements. A ground fault circuit interrupter, or GFCI, is a device that protects people from electric shock by monitoring the current balance in a circuit. If a ground fault is detected, the GFCI quickly trips the circuit, interrupting the flow of electricity. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. An arc fault circuit interrupter, or SI, is a device that protects against fires caused by arcing faults in electrical wiring. SIs detect the unique characteristics of arcing faults and trip the circuit, preventing the arc from igniting nearby materials. SIs are required in many locations, such as bedrooms and living rooms. Electrical safety standards, such as those published by the National Fire Protection Association, or NFPA, and the Institute of Electrical and Electronics Engineers, or IEE, provide guidelines for safe electrical practices. Electricians should be familiar with these standards and follow them to ensure the safety of themselves and others. It's important to consider renewable energy integration. Solar photovoltaic systems convert sunlight into electricity using solar panels. Electricians who install solar systems must understand the principles of photovoltaic technology, as well as the requirements of the NEC for solar installations. Wind turbine systems convert wind energy into electricity using wind turbines. Electricians who install wind turbine systems must understand the principles of wind energy, as well as the requirements of the NEC for wind turbine installations. Energy storage systems, such as batteries, can be used to store energy generated by renewable sources or to provide backup power during outages. Electricians who install energy storage systems must understand the different types of batteries and their charging and discharging characteristics, as well as the requirements of the NEC for energy storage installations. Understanding smart grid technologies is also important. Smart meters are electronic devices that measure electricity consumption and communicate data to the utility company. Electricians who install smart meters must understand the communication protocols and data formats used by smart meters, as well as the requirements of the NEC for smart meter installations. Demand response programs allow customers to reduce their electricity consumption during peak demand periods in exchange for incentives. Electricians who participate in demand response programs must understand the control systems and communication protocols used to manage demand response loads. Electric vehicle charging stations provide electricity for charging electric vehicles. Electricians who install electric vehicle charging stations must understand the different types of charging stations and their electrical requirements, as well as the requirements of the NEC for electric vehicle charging installations. Proper grounding ensures a safe path for electricity in case of a fault, preventing electrical shock. Bonding connects non-current carrying metal parts to create a low impedance path for fault current. Always refer to NEC Article 250. Ground fault circuit interrupters protect against electrical shock by detecting imbalances in current flow. Arc fault circuit interrupters prevent fires by detecting and interrupting dangerous electrical arcs. Overcurrent protection devices, like circuit breakers and fuses, protect circuits from overloads and short circuits. Calculating voltage drop ensures efficient power delivery and prevents equipment malfunction. Use the formula voltage drop equals 2 times length times current times resistance divided by 1000 for single-phase circuits. For three-phase circuits, use voltage drop equals 1.732 times length times current times resistance divided by 1000. Conduit bending requires precision to ensure proper wire installation. Use conduit benders and follow manufacturer instructions. Wire pulling involves safely installing conductors through conduits. Use lubricants to reduce friction and prevent damage to insulation. Cable tray systems provide support and routing for cables. Install cable trays according to NEC guidelines and manufacturer specifications. Fiber optic cabling is used for high-speed data transmission. Handle fiber optic cables with care to prevent damage and maintain signal integrity. Data cabling, such as Cat5e and Cat6, is used for network communications. Terminate data cables properly to ensure reliable network connections. Programmable logic controllers are used for automation and control systems. program and troubleshoot PLC using specialized software and programming languages. Variable frequency drives control the speed of electric motors. Install and configure VFD to optimize motor performance and energy efficiency. Power quality analysis identifies and resolves power quality problems. Use power quality analyzers to measure voltage, current, harmonics, and other parameters. Infrared thermography detects hotspots in electrical equipment. Use infrared cameras to identify potential problems and prevent equipment failures. Electrical safety audits identify and correct electrical hazards. Conduct regular safety audits to ensure compliance with safety regulations. Lockout/tagout procedures prevent accidental energization of equipment during maintenance. Follow lockout/tagout procedures to ensure worker safety. Personal protective equipment, or PPE, protects electricians from electrical hazards. Use appropriate PPE, such as safety glasses, gloves, and arc-rated clothing. Continuous education keeps electricians up to date with the latest technologies and codes. Attend training courses and seminars to enhance your skills and knowledge. Mentorship provides guidance and support for aspiring electricians. Seek out mentors who can share their experience and expertise. Professional organizations, such as the International Brotherhood of Electrical Workers, or IBU, and the National Electrical Contractors Association, or NECA, offer resources and support for electricians. Join professional organizations to network with other professionals and advance your career. It's important to consider electric heat calculations. Firstly, calculate the heating load of the space. Use Manual J from the Air Conditioning Contractors of America, or CA, to determine the heating load in British thermal units per hour, or BTU per hour. Secondly, determine the voltage and amperage requirements. Electric heaters are typically available in 120 volts, 208 volts, 240 volts, 277 volts, and 480 volts. Choose a heater that matches the available voltage and calculate the amperage using the formula amps equals watts divided by volts. Thirdly, size the circuit conductors and overcurrent protection. Use NEC Table 310.16 to determine the ampacity of the conductors based on the amperage of the heater and the type of insulation. Size the overcurrent protection device, such as a circuit breaker or fuse, to protect the circuit from overloads and short circuits. Fourthly, select the appropriate wiring method. Choose a wiring method that is suitable for the environment and the type of conductors being used. Common wiring methods for electric heaters include conduit, cable, and surface raceway. Fifthly, install the heater according to manufacturer's instructions and NEC requirements. Follow the manufacturer's instructions for installing the heater and ensure that all connections are made properly. Ground the heater according to NEC requirements to protect against electrical shock. The electric heat insulation should be inspected and tested. Inspect the installation to ensure that it meets all applicable codes and standards. Test the heater to verify that it is operating properly and that all safety devices are functioning correctly. Consider the following electric heat troubleshooting tips. If the heater is not working, check the power supply to ensure that the circuit breaker is not tripped or the fuse is not blown. If the heater is overheating, check the thermostat to ensure that it is set correctly. Clean the heater to remove any dust or debris that may be blocking the airflow. If the heater is making unusual noises, check the fan motor to ensure that it is not damaged or worn out. Contact a qualified electrician for assistance with any complex electrical problems. Electrical diagrams are essential for understanding and troubleshooting electrical circuits. Single-line diagrams show the basic components and connections of an electrical system. Wiring diagrams show the detailed wiring connections between components. Ladder diagrams are used to represent the logic of control circuits. Motor control circuits are used to start, stop, and protect electric motors. Forward/reverse control circuits allow a motor to operate in both directions. Reduced voltage starters reduce the starting current of large motors. Three-phase motor connections include Y and delta configurations. Transformer connections include delta-delta, Y-Y, delta Y, and Y delta configurations. Control transformers provide a lower voltage for control circuits. Current transformers are used to measure current in high voltage circuits. Potential transformers are used to measure voltage in high voltage circuits.